This is section 8.5 of Honors Algebra 2, the remainder and factor theorems. Two theorems that will allow us to factor and solve higher order, higher degree polynomial equations. So we know how to factor and solve quadratic equations. What if we want to solve polynomials that are of higher degree, like cubic or quartic or quintic, or polynomials of degree 6 or 7 or 8? We can solve them using these two theorems and theorems we're going to get in the next video as well. To start with, this relationship that I've written here, that the dividend equals the quotient times the divisor plus the remainder, is something called the division algorithm. And it's true if you are dividing numbers or polynomials, that what we're dividing, which is the dividend, equals the quotient, which is our answer, times the divisor, what we were dividing by, plus the remainder. So let's take this polynomial, p of x, which is equal to 2x cubed minus 7x squared plus 5x minus 1. I've got two questions here. What is p of 3? What is the value of p when x is 3? So p of 3 means we're going to plug in 3 for x. So we'll have 2 times 3 cubed minus 7 times 3 squared plus 5 times 3 minus 1. And we can just work that out. 3 cubed is 3 times 3 times 3, which is 27, times 2 is 54, minus 9 times 7, which is 63, plus 15 minus 1. If you work it out, it's 5. Okay, p of 3 is 5. 54 minus 63 plus 15 minus 1. What's the remainder when we divide p of x by x minus 3? Well, remember, I could actually do the long division, or I can use synthetic division and take 3 and divide it into the coefficients 2, negative 7, 5, negative 1. Bring down the 2, multiply by 3, add, multiply, add, multiply, add. I get a remainder of 5. Hey, wait. That was the same thing that I got p of 3 to be. So p of 3 had the same value as the remainder when I divided by x minus 3. Is that a coincidence? Absolutely not. So let's see why. I could write, according to the division algorithm, I could write p of x as the quotient, which I know is 2x squared minus x plus 2, because that's what I got as my answer when I did the synthetic division. So 2x squared minus x plus 2. The quotient times the divisor, which is x minus 3, plus the remainder of 5. I can write that according to the division algorithm. Well, what is p of 3 then, evaluating that? Well, I'd have 2 times 3 squared minus 3 plus 2 times 3 minus 3 plus 5. And I don't really care what the 2 times 3 squared minus 3 plus 2 is, because it's going to be multiplied by 3 minus 3, which is 0. This whole thing goes away to be 0, and p of 3, according to this, is just 5, which was the remainder. So that's a loose proof of why p of 3 is going to be the same as the remainder when I divide by x minus 3. And in general, that same relationship is true. In general, if q of x is the quotient and r is the remainder, when the polynomial p of x is divided by x minus c, then p of c equals r. The value of the polynomial at c is equal to the remainder when I divide by x minus c. This is called the remainder theorem. It means that p of x equals q of x times x minus c plus p of c, where q of x is the polynomial of degree n minus 1. So this is just the division algorithm where I replaced r with p of c, because I know that the remainder when I divide by x minus c is going to be equal to the value of the polynomial at c. Here's a little proof of that theorem. Because what's the good of a theorem if we are just told that it's true? We need to understand that it's true. We know that p of x equals q of x times x minus c plus r. That's the division algorithm. So that means p of c, if I plug in c for x, is going to be q of c times c minus c plus r. Well, c minus c is 0. So this is q of c times 0 plus r. And q of c times 0 is 0 plus r means r. So p of c equals r. And that's exactly what the remainder theorem said I should get. So let's take an example of how we can use this. Find the value p of negative 4 for the polynomial p of x equals x to the fourth minus 14x squared plus 5x minus 3. Well, I could do this just by plugging in negative 4 for x and evaluating it. But what the remainder theorem does is gives me a second way to do this, and that's to use synthetic division. Because if I take the remainder when I divide by negative 4, I'll get the value of the function at negative 4. So I'll take negative 4, and I'm going to divide that using synthetic division. I've got 1. Notice I'm missing an x cubed, so I have to put in a 0 for that. I've got negative 14, and I've got 5, and then I've got negative 3. I bring down the 1, I multiply by negative 4, I add, I multiply by negative 4, I add, I multiply by negative 4, I add, I multiply by negative 4, I add. What's the remainder? 9. That means that p of negative 4 is 9. And I'm done. So in some ways that's faster when you've got a long polynomial like that, because I don't have to actually take negative 4 to the fourth power and negative 4 squared and multiply it by 14. The synthetic division can be a lot faster and a lot quicker. Now the remainder theorem on its own is not all that useful, because again I have another way of doing that. I could have just plugged in negative 4 and evaluated it. But the remainder theorem is most useful when it leads to another result. So it's most useful in one particular case, when the remainder happens to be 0. So that is, there is some value r for which p of r is equal to 0. The remainder is 0. That means when I plug in r to the polynomial, I get 0, according to the remainder theorem. If the remainder is 0 for some value r, then p of x equals q of x times x minus r plus the remainder, capital R. That's just the division algorithm. That becomes, when the remainder is 0, p of x equals q of x times x minus r plus 0. Well, adding 0 doesn't do anything, so that's the same as p of x equals q of x times x minus r. That means when the remainder is 0, x minus r is a factor of the polynomial. So we get what's called the factor theorem. The polynomial p of x has x minus r as a factor if and only if r is a root of the equation p of x equals 0. So I picked r because it's going to mean that it's a root. Being a factor, remember, means that it divides evenly into it. So it divides into it in a way that gives us no remainder. So this makes sense. And it's an if and only if. So if you remember from geometry, an if and only if I conditional. It goes both directions. So I need to prove both directions. So let's take, if r is a root of p of x equals 0, so that's actually the reverse direction. We'll do that one first, because it doesn't matter which order we go in. If r is a root of p of x equals 0, then by definition of a root, p of r equals 0. A root means it's a value of the function when the function is equal to 0. It's a value for the variable that will give me a value of 0 for the function, in other words. So if the function equals 0, this is a solution. That's what it means to be a root. By the remainder theorem, we get the above result, that p of x equals q of x times x minus r. Therefore, x minus r is a factor of p of x, because I can write x minus r times another polynomial. Alright? So the other direction. If x minus r is a factor of p of x, then p of x equals q of x times x minus r for some polynomial q of x. That's what it means to be a factor. I can take my original polynomial and break it up as a product of the two smaller polynomials, where x minus r is one of those smaller polynomials. And thus p of r is, if I just plug in r for x, q of r times r minus r, but r minus r is 0. That's q of r times 0, which is 0. That means p of r equals 0. Therefore, r is a root of p of x equals to 0, because when I plug in r, I get 0 for the function. That makes it a root. So this is incredibly useful, and here's why. If I take the polynomial p of x equals x to the 12th minus 3x to the 8th minus 4x minus 2, I have no way of solving that or factoring that using what we've done up to this section. But using this section, I can do it to an extent. And I'll need the next section to be able to do it completely. But determine whether x plus 1 is a factor of that polynomial. I have no way of factoring that other than to use the factor theorem that I just did. If x plus 1 is a factor, then p of negative 1 equals 0. And the other result from the factor theorem is the reverse direction, that if p of negative 1 equals 0, then x plus 1, which remember is really x minus a negative 1, is a factor. Okay, so if I want to know if x plus 1 is a factor, all I need to do is take p of negative 1 and see if that is equal to 0. If it is, then x plus 1 is a factor. Right? So I take p of negative 1. And I could use synthetic division. Negative 1 is easy to take to a bunch of powers, so I'll go ahead and do that the normal way here. Okay, negative 1 to the 12th is an even power, so that's a positive 1, minus 3 times positive 1, because again it was to the even power, minus 4 times negative 1, that's plus 4, minus 2. So that's 1 minus 3, it's negative 2, plus 4 is positive 2, minus 2 is 0. So since p of negative 1 equals 0, x plus 1 is a factor. So yes, it is. Number 2, find a polynomial equation with integral coefficients that has 1, negative 2, and 3 halves, 3 over 2 as roots. Okay, if they're going to be roots, and according to the factor theorem, x minus 1, x minus a negative 2, or plus 2, and x minus 3 over 2 must all be factors. Okay? Now let's take the x minus 3 over 2 and let's deal with the fraction, because I want integral coefficients, so I want all of my coefficients to be integers and not fractions. Well, another factor that has 3 over 2 as a root would be 2x minus 3. So I can replace x minus 3 over 2 with 2x minus 3. So notice the numerator stays where it is, and I just take the denominator and I put it in front of x. That has a factor, or that has a root, sorry, of 3 over 2. So I can use that one instead, and that will give me integral coefficients. So here's how I can make an equation. I can just take 0 equals x minus 1 times x plus 2 times 2x minus 3, and that's an equation that has integral coefficients with 1 as a root, negative 2 as a root, and 3 over 2 as a root. So we can multiply that out, and we'll get 2x squared, 2x cubed minus x squared minus 7x plus 6, if you were to FOIL that all out. So that is a polynomial equation with integral coefficients, because all of its coefficients are integers, that has 1, negative 2, and 3 over 2 as roots. Guaranteed. Because if they're roots, then x minus that number is a factor. So I formed that by multiplying out those factors. Now there are actually an infinite number of polynomial equations that have those three things as roots. I would just have to take a times this whole thing, where a is any other number, Any number other than 1 will give me a different polynomial equation than the one I have. And a could be any number at all. It could be a complex number. It could be a real number. It could be a rational and irrational number. It doesn't matter. I'm going to get an equation that has those same roots. So that's awesome. Number 3. Solve x cubed plus x plus 10 equals 0 given that negative 2 is a root. Okay? If I know negative 2 is a root, then that means x minus a negative 2, x plus 2 is a factor. So it means that if I divide by negative 2, I'll have a smaller polynomial, that quotient, that is also a factor. So if I take my coefficients, 1, I'll put a 0 to hold my place for x squared, and 1, and then 10. I bring down the 1, multiply by negative 2, add, multiply by negative 2, add, multiply by negative 2. I get a remainder of 0, which is good. I need to, since negative 2 is a root. So that's good. I better get 0. But I also have this quotient, q of x, which is x squared minus 2x plus 5. That's the quotient I got when I divided. And I know that x cubed plus x plus 10 can be written as x squared minus 2x plus 5 times x plus 2. I divided by x minus 2, so x plus 2 is a factor. And the answer was x squared minus 2x plus 5. So my original polynomial can be written out like that. So now if I can just factor x squared minus 2x plus 5, or solve it, if it can't be factored, then I'll have solutions to the whole equation. Alright? So let's solve x squared minus 2x plus 5. Well, it can't be factored, so we can use the quadratic equation. I'm sorry, the quadratic formula. X equals negative b, so that's positive 2, plus or minus the square root of b squared, which is 4, minus 4 times 1 times 5, all over 2 times 1. So x equals 2 plus or minus square root of 4 times 5 is 20, 4 minus 20 is negative 16, and all over 2. So x equals square root of negative 16 is 4i. So when we divide everything by 2, we'll have 1 plus or minus 2i. And don't forget that negative 2 is also a solution. So my solutions are negative 2, 1 plus 2i, 1 minus 2i. And I was able to then solve a cubic equation using the results of this section, using essentially the factor theorem. Here are your immediate practice problems. Number 1, is x plus 3 a factor of that really long 5th degree polynomial? All you have to do is check to see if when you divide by negative 3, do you get a remainder of 0? If so, it's a factor. If you don't, it's not a factor. Number 2, find a polynomial equation with integral coefficients that has 3, negative 2, and 4 as roots. So if those are roots, you know x minus each of those numbers is a factor, and multiply those out, set it equal to 0, and that will be your polynomial equation. That is the end of section 8.5.